print a couple copies. Have one that you bring, one at your work, and then basically what we do that Wednesday is we will go over the exam. It'll take long, it'll take about an hour, and we'll answer any questions that you may have. The following Wednesday will be exam day, okay?
How many questions?
20 questions,
Oh, okay.
nice and simple.
Yeah, right. Nothing is simple in
All
chemistry.
right, well, we're dealing with two different classes of compounds. We will call these molecular compounds and ionic compounds. Molecular compounds, we'll see in just a minute, that the atoms in the compound actually share electrons. They share what we will call valence electrons to form chemical bonds. This is methane, natural gas, we've seen this before. And what this bond here means is that carbon and the hydrogen are sharing a pair of electrons. The other type of compounds are ionic. In ionic compounds, you don't share electrons. Oh, here's another example of a molecular compound. When we form bonds between different atoms, we can form either a single bond like these. This is a double bond, so there's two pairs of shared electrons here, or even triple bonds. We'll talk about that in just a bit. Ionic compounds don't share electrons. In an ionic compound, you will totally transfer one or say up to 3 electrons from one atom to another. Now this is sodium chloride. When we make sodium chloride, the sodium will lose 1 electron and donate it to the chlorine. That makes the sodium positive and the chlorine negative. These things are held together by electrostatic force. So here, the two, the positive and the negative, just stick together. They stick together in a very regular way, and that's why we get geometry, very nice geometry in our crystals. Now let's talk a little bit about where these electrons come from and how we go about forming bonds. This is carbon. We've seen carbon before. We have a periodic table, yes we do. Carbon is in the second period. Again, that means our first period is full. When we say that, we're talking about the core electrons here. Core electrons are the ones that are closest to the nucleus, and they're the least interesting because they don't do anything. They just sit there. So the 1s here is totally full. The 2s electrons and 2p electrons are out here. There's a total of 4. And we know that because there's 1, 2, 3, 4. And these are what we call the valence electrons. These are high energy, they're the outer electrons, and they're what we use to make chemical bonds. In order to help visualize chemical bonding, a guy named Lewis, very long time ago, about 1800s, late 1800s, actually came up with a method to show how you make simple chemical bonds. And this is a Lewis dot structure, it's called. What you do is you start off with the chemical symbol of whatever element you have. So let's do carbon. Carbon is here. Again, it's in the 4th period here, a 4th group, 2nd period. So it will have 1, 2, 3, 4 valence electrons. We draw our symbol. Again, these high energy electrons, the one in the 2nd period, are our valence electrons. Now Lewis said what we do is we put these electrons around the atom. We're going to put them in one at a time. After you get more than 4, you pair them up. So with carbon, since we have 4, we would put them in this way. And this is the Lewis structure then for carbon. Let's go ahead and do another example. Again, after we get 4, we start to pair them up. So let's do fluorine. Fluorine, again, is in our second period, and it's all the way down here in group 7. So it will have 1, 2, 3, 4, 5, 6, 7 valence electrons. We start off with our symbol. Next, we're going to put 4 electrons around it. Then we're going to put the remaining 3 so that we pair them up. Now, does it matter if I put my single electron here, here, or wherever? No. Doesn't matter at all. Lewis dot structures are just a nice, simple bookkeeping method for doing chemical bonds, ions, and things like that. When you are doing a Lewis dot structure, remember I said it was so nice just to number our main groups here 1 through 8. That's because the group numbers here, 1 through 8, tell us the number of valence electrons, nice and simply. Hydrogen, 1, magnesium would be 2, boron 3, here we're at silicon, group 4, we have 4 electrons. Phosphorus is going to be 5, selenium here is 6, chlorine is 7, and these guys, the noble gases, will have complete shells. So this has a full set of 8. All right. When we're dealing with ions, like in an ionic compound, what we're going to do is start off with our basic Lewis structure. And we're going to either add or subtract electrons. Now, if we add electrons, that means we're going to make something that is negative, right? Because we'll have more electrons than protons. If we take away electrons, it's going to be positive. The words are positively charged ion is a cation, negatively charged is an anion. So let's look at chlorine. Chlorine is down here in the 3rd period. It's in the 7th group. So it's going to have 7 valence electrons, right? Put them around. Again, it doesn't matter where we put them. It's just bookkeeping. Now, to make an ion, the chloride anion, we need to add 1 extra electron. When we do this, we now have 8 electrons around it, and the chloride ion will have a negative charge. It has 1 more electron than it does proton. You'll note that since we have 8 electrons around the chlorine now, that's equivalent to the inert gas argon. Remember, inert gases don't react. They don't react because their valence shell is completely full. All right, let's go ahead and do this for sulfide dianion. Step 1, you look at your periodic table and you find sulfur. Well, here it is. Its atomic number is 16, and it's in group number 6. So it's going to have 6 valence electrons. Start off by putting the valence electrons around it. Remember, if we have more than 4, we have to pair them. Now to make the dianion, what we do is add 2 more electrons, one here, and we have to show that this is a -2 anion. Typically, this is written as 2 minus. If you write it as -2, I don't care. So it doesn't matter. Go ahead and look at nitrogen. Nitrogen forms the nitride anion. Nitrogen is here in group 5. Symbol is N. So you make your chemical symbol, and then we're going to put 5 electrons around it. We tend to say that this nitrogen has an unshared pair of electrons. That's the terminology we use. We'll see that when we build compounds. All right, to make the trianion, all we have to do is add 3 electrons, and again show the charge.
And you say you can put those electrons anywhere?
Well, yeah, but, well, in a properly drawn structure, you symmetrically place them above. You know, don't.
I mean,
Pile 'em
well,
up.
I know, I'm just saying like
Yeah.
around.
Yeah, it doesn't matter how you do it, no.
Okay.
All right, let's look at one more. How about the sodium cation? Let's find sodium. It's right here in group 1, symbol Na. Start off by drawing the symbol. Because it's in group 1, it will have 1 valence electron. Now to make the sodium cation, the cation is positively charged, right?
Mhm.
So we have to simply take this electron away. There it goes. Now again, let's think a little bit about what we've done here. We started off with chlorine, right here. We added an electron to make the chloride anion. When we did that, I said that this had the same electron configuration as argon. We totally moved from here to here and filled up the shell. When we did sulfur, we added 2 electrons. We started here, and by gosh, we're all the way over here to argon again, aren't we? Sodium. Well, sodium, we started here, and we lost this electron. What that does is move it up to the previous period and down here to neon. So this has the same configuration as neon. The trend here is to totally fill up the outermost shell. It'll hold 8 electrons, and this is called the octet group. When you're building structures, you try to fill up the outer shell so that you have 8 valence electrons. That makes it just like the inert gas, and that means it's done reacting. All right, let's go ahead and do this with chlorine, and let's show how we make a chemical bond. This is chlorine, like we said, it's in group 7, so it has 7 valence electrons. Chlorine, as we find it, as it exists in nature, exists as CO2. 2 chlorines stuck together. The bond between them is called a covalent bond. And like I said in the intro, covalent bond means you share electrons. The way this happens, here's our chlorine. Let's bring another one up to it. When we do this now, if you look at our two chlorine atoms, we are sharing these electrons in the middle. That's a bond. If we count up the number of electrons around each chlorine, we see that there are 2, 4, 6, 8 on this one, and 2, 4, 6, 8 on this one. You count the shared electrons, it's, nice, happy sharing. You count the shared electrons for each of the atoms. Another way to draw this, when you have 2 electrons in a covalent bond, instead of drawing the little dots in between it, people get really tired of doing dots, you can use a horizontal line. The dash, when you draw it like this, is meant to tell you that this represents 2 electrons in a covalent bond. The 2 electrons are shared by these 2 atoms. Any questions? All right, let's go ahead and build a molecule. This is ammonia, NH3. When you draw ammonia, nitrogen is going to be in the middle, and your hydrogens are going to be around it. First thing you want to do is find your elements on the periodic table. Nitrogen is here in group 7, group 5, atomic number 7. So it will have 5 valence electrons. Hydrogen is in group 1, so it will have 1 valence electron. So you start off when you're building your molecule just by putting the atoms, and then you're going to rearrange them so that we have 8 electrons around our atoms. Now the exception there is hydrogen, because hydrogen only has the 1s orbital, doesn't it? So its inert gas is helium, and that has 2. So hydrogen, you want to give 2 electrons to. Everything else, we're shooting for 8. All right, so we have our 1 nitrogen here with 5 electrons. We have 3 hydrogens. Step 2, we're going to scooch them together. When we scooch them together, we can clearly see that we can form a bond here, a bond here, and a bond here. This is our unshared pair of electrons. If we look at our nitrogen here, remember we count all of these shared electrons, so it has 2, 4, 6, 8, and each hydrogen has 2. If we draw this using our dashes, it would look like this. Again, we refer to this as a simple single bond. Now, on your exam, you are going to have to draw a Lewis structure. We're going to do this the same way. Again, what you do is find the atoms on the periodic table, figure out how many valence electrons they have, scooch them all together, and rearrange them in order to make 8 electrons, if possible. If it's a hydrogen, give it 2. Let's do another. Molecular nitrogen. This one's a little more difficult. Nitrogen, as a gas, exists as N2. So 2 nitrogens stuck together. It's a very, very unreactive gas. We'll see why in just a minute. Step 1, find our atoms here. It's in group 5. And this is the electron mess we have to work with. Now, what we have to do is to pair these electrons up, rearrange them, so that we can make 8 valence electrons around each nitrogen. Now, just to show you that I can do it too, I hope. There it is. This is 2 nitrogens, and they each have 5 electrons. Now, it's really obvious that we can share these two right here and make a bond, right? But if we just did that and left it alone, we would have 1, 2, 3, 4, 5, 6 electrons. That's not 8, is it? Remember, we want to shoot for 8. But in a case like this, we can remedy that by moving some of these electrons. Let's move this up to here. And move this guy up to here. Now, if we share 2 sets of electrons, this nitrogen would have 2, 4, 6, 7 electrons, and so would this one. Still not quite 8, is it? So in order to get to 8, we have to take this guy, move it in, take this guy, move it in, and presto, we have 6 shared electrons, so 6, 7, 8, 6, 7, 8. If you look at what we just drew, once again, this nitrogen has 8 electrons. This nitrogen also has a full 8 electrons. What we've done here is make a triple bond. If we drew this out using dashes, we would show it this way. This means what you see when you see something like this is these 2 nitrogens are held together by 3 bonds, each bond consisting of 2 electrons. This is why nitrogen is so stable, actually, because the triple bond is very strong. We have 3 bonds holding this thing together. That makes nitrogen a very unreactive molecule. Any questions? All right. I said that we were going to deal with 2 types of compounds, molecular compounds and ionic compounds. Molecular compounds are those that form covalent bonds, just like we did with nitrogen and with ammonia. The way to tell if you are going to make a molecular compound or an ionic is simply to follow the very simple rule of thumb. If your compound consists only of nonmetals and semimetals, or semimetals, either one, it will be molecular. If it has a metal in it at all, it will be ionic. We looked at ammonia, had 1 nitrogen, 3 hydrogens. They're both nonmetals, therefore molecular compound. We looked at nitrogen gas, 2 nitrogens, again they're both nonmetals, molecular compound. Earlier, we saw methane, 1 carbon, 4 hydrogens, molecular. And we saw sodium chloride. Sodium's a metal. Chlorine's a nonmetal, but if you have a metal in there, it will be ionic. Remember, the semimetals here are in between metals and nonmetals in terms of reactivity, in terms of chemical and physical properties. These are semiconductors, etc. But again, they form molecular compounds. There are exceptions, but especially with these. But right now, for this class, they're molecular. All right. Magnesium chloride. Is this going to be molecular or ionic?
Ionic.
That's right. What you do is find them. Magnesium is here. It's a metal. Chlorine's a nonmetal. But if you have a metal in your compound, it is not molecular. It will be ionic. Hydrogen fluoride. Well, hydrogen is here. It's our nonmetal. Fluorine is here. It's a nonmetal. Therefore, this is a molecular compound. Silicon tetrachloride. Well, silicon lives right here. It's green. It's a semimetal, isn't it? Chlorine is a nonmetal. That means that silicon tetrachloride is molecular. Sodium bromide, well, just like sodium chloride. Sodium's a metal. Doesn't really matter what it's attached to. If it's a metal, it is not molecular, it is ionic. And finally, let's look at S8. Sulfur exists in many forms, but just plain old sulfur out of the ground actually exists as a ring of 8 sulfur atoms. Is this going to be a covalent compound, or is it going to be an ionic compound? Well, we find sulfur right here. It's a nonmetal. So these, the bonds in all of S8, are molecular. It's actually an interesting little cute compound. Looks like a crown of some sort, but molecular compound. All right, go ahead and look at a list. I'll hush for a minute and just decide if these are molecular or ionic. This is nickel chloride. We look at our periodic table, we find nickel. It's down here in the transition metals. Therefore, this is a metal and a nonmetal. It is an ionic compound and not molecular. The term not molecular is used in lots of books instead of ionic. Because sometimes ionic is a all-encompassing term, and simply not molecular kind of means we don't have covalent bonds. But I'll use both. Dihydrogen monosulfide, commonly known as hydrogen sulfide. It's the stinky stuff in well water. Hydrogen is a nonmetal, sulfur is a nonmetal, This is a molecular compound. Silicon tetrahydride. Silicon is a semimetal. Hydrogen is a nonmetal. This is molecular. Sulfur trioxide. Sulfur and oxygen are both nonmetals. Calcium hydride. Soon as you see the metal, it's a dead giveaway, isn't it? This is an ionic compound and is not molecular. Quickly, let's look at one more list and do the same thing. Cesium is in group 1. Down here, oxygen is way over here in group 6. We have a metal, a nonmetal, and it's an ionic compound. Diiodide heptaoxide. And we're going to learn how to name these. Isn't that exciting? Iodine is in group 7. Oxygen is in group 6. They are both nonmetals. It is molecular. One oxygen and 2 fluorines. Oxygen difluoride. Nonmetal, nonmetal, molecular. We've seen methane. Actually, technically it would be carbon tetrahydride, but nobody would have an idea what that was. It's called methane. But again, carbon and hydrogen are both nonmetals. And finally, sodium chloride. As soon as you see the sodium, you know this is ionic. Any questions? All right. There's another type of compound we're going to talk about as far as ionic compounds go, that will contain a metal, or at least a cation, but they are paired with what's known as a polyatomic ion. Polyatomic ion is a group of atoms that are held together by covalent bonds. So that's molecular. But that group is charged. It'll either be negative, most commonly, or positive. An example, strontium sulfate. Strontium we'll just represent as a little ball. This is a group 2 metal. It will form a +2 ion. Sulfate consists of 1 sulfur and 4 oxygens. They're all held together by covalent bonds, but the group, SO4, all of this, has a -2 charge. So just like we pair up a sodium and a chloride, here we can pair up a strontium and a sulfate, and we make what's called strontium sulfate. In sodium chloride, we had the sodium and the chloride like that. Same sort of thing here. We have the strontium and the sulfates held together by electrostatic attraction. Now, the bad news is that there are a lot of polyatomic ions, and they're actually very important in chemistry. This is a table, and it's got a lot of things on it. Do you have to know them? Actually, yeah, kind of, most of them anyway. So let's go through them, and I'll actually show you a trick for remembering some of them anyway. The trick, if your polyatomic ion contains oxygen, we're going to define what's called the parent. Then we're going to add or subtract oxygens. The neat thing is that all of these will have the same charge. They'll just have different numbers of oxygens, and of course different names. Our parent, we're going to take the root name, like sulfur would be sulf, okay? And we're going to add 8 to it. So that's sulfate. That's our parent. If we add one more oxygen to it, we would call this a per-sulfate. If we take one oxygen away, it would be a sulfite. If we take 2 oxygens away, it would be a hyposulfite. All of these, however, will have exactly the same charge. So really what you have to remember in each of the major groups is who's the parent, and then you just change the prefixes and add or subtract oxygens, all with the same charge though. So let's look at the list here. It's a little overwhelming perhaps. These are nitrogen-containing ions. Our parent here is nitrate, NO3. Charge is -1. If we take one oxygen away, we make it nitrite. These are the only 2 you need to worry about. The only positive polyatomic ion we're going to deal with is NH4 plus ammonium. Here it is. This should remind you a lot of what we saw for methane. The same geometry, nitrogen in the middle, 4 hydrogens, and a plus charge. This, by the way, is nitrate, nitrogen in the middle, 3 oxygens around it. Sulfur containing, we just did sulfate and sulfite. Those are the only 2 you need to worry about there. We can also take and add a hydrogen to one of these oxygens. When we do that, we simply call it hydrogen sulfate or hydrogen sulfite. And since the hydrogen comes in with a plus charge, comes in as a plus, the charge will drop down from -2 to -1, -2 to -1. Phosphorus, phosphate, phosphite, hydrogen, phosphate, dihydrogen, phosphate. We can do the same thing with phosphite. This is dihydrogen phosphite. -3s, we had 1 hydrogen, drops to -2, 2 hydrogen, drops to -1. Again, our parent is phosphate. Carbon, CO3 is carbonate. There is no carbonite. That was in Star Wars. Put a hydrogen in front, we get hydrogen carbonate. This is also called bicarbonate. Sodium bicarbonate is actually sodium hydrogen carbonate. These guys we won't deal with very much yet. We'll see acetate a bit later. You should probably know cyanide, Cn-. Here's our beautiful set for chlorine. Chlorate is our parent. They're all -1. Add 1 more oxygen, we get perchlorate. Take 1 oxygen away, we get chlorite, and then hypochlorite. Boron, borate's all you have to worry about. Hydronium and hydroxide. We will deal with those when we do acids and bases. And these are other things that you see sometimes: permanganate, chromate, dichromate. Permanganate is the one you might see most often, MnO4, single negative charge. This is a potassium permanganate, is a rich, deep purple, widely used to kill bacteria, to oxidize things in dirty water, etc. It's a water purification chemical. All right, let's go and look at one of our polyatomics here, just so that you understand how it's put together. Let's draw the structure of the chlorate anion. Now again, you have to do this on the exam, so go ahead and try to get started here. You're going to find the two. Chlorine's going to be in the middle. Going to put 3 oxygens around it and give them their appropriate valence electrons. Chlorine is here in group 7, so we have a chlorine with 7 little dots. Because it has 7 dots, we're going to have 3 pairs and 1 single. Oxygen is in group 6, so it's going to have 6 electrons around it. 2 of them will be paired, 2 sets will be paired, and 2 will be single. So what we're looking at is this. Here's our oxygens, 2 pairs, 2 singles, and our chlorine has 1, 2, 3, 4, 5, 6, 7. All right, remember, Lewis structures are just bookkeeping, aren't they? So we can rearrange them in order to form our single bonds. As I look here, we have 3 electrons between these guys, don't we? Only 2 electrons can go in a bond. Only 2. Therefore, let's take one of these electrons and just move it up to here. Let's take one of these electrons, move it up to here. So we get something like that. Now we can look at this and say, okay, we can make a nice single bond here, can't we? Make a nice single bond here, but we only have 1 electron here. However, chlorate is an anion, isn't it? So we're going to put in 1 more electron. And it always goes on the central atom. So here comes our electron. And now this group is going to have a negative charge. Now we can scooch everything together. We can make 1 bond here, 1 bond here, 1 bond here. Each oxygen will have 8 electrons. A chlorine will also have 8 electrons. And this is how we would draw it as a line bond structure. This is how we put together and make polyatomic ions. Put them together, add electrons, always on the central atom, and then make your bonds. Any questions? Now there's a tutorial on drawing Lewis structures, but it's not one that you can get credit for because you just draw them on scratch paper. But there's some interesting compounds, and it will lead you through the steps of drawing it out. Uses a slightly different method, one where you add up the total number of valence electrons, distribute them, and blah, blah, blah. But it still works. You know, whichever one is easiest for you, you can do. Now, you know, I said that when we make structures, that we shoot to make the central atom have 8 electrons. That's the octet rule. There are, however, many, many, many exceptions to the octet rule. This is one example. This is SF4. If you sit and you look at the electrons around this sulfur, it will have 2, 4, 6, 8, 10. This is the geometry of it. It's actually called seesaw geometry. You lay it on its side, it kind of goes like this. But see, chemists could be cute. But it has 10 electrons. Let's look and see how in the world this happens. I'm going to do SF4 here. Sulfur, right here, third period, 6 groups. So it will have 6 valence electrons, right? We have 4 fluorines to put around it. And they're each going to have 7. So what we're dealing with is this. Whoa, there's a lot of electrons. Lots of little dots. But as you look at this, okay, we can make a bond here, can't we? We can make a nice bond here. But here we have 3 electrons between each of them. And that's bad, because only 2 can be in a bond. So the way to draw the Lewis structure here is to say, okay, too many electrons. I'm just going to take 2 of these, and I'm going to put them in somewhere, put them in storage. So let's take 2 electrons, any 2, and kazook, they're down here somewhere. Okay? Now that we've done that, life is so much simpler because we can make a bond here, 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 and here. Right? That's good. But we really can't just hide the electrons down here on the floor somewhere, can we? They belong on the sulfur. So after we draw our bonds, we just put the electrons back. So again, this sulfur has 2, 4, 6, 8, 10 electrons. This is called valence expansion. Now, valence expansion happens for compounds in the 3rd period and below. Anything in the first 2, you can't get above 8. But anything in the 3rd period and below can form multiple, actually up to 14 electrons around the central atom. Again, this is what it looks like. Here's the pair that we put back. And here's our 4 covalent bonds and 1 unshared pair of electrons. Yeah?
So all the ones that are going to be in storage are going to be around the central one.
Right, only around the central.
Okay.
Let's do another one that's not quite so exotic. Boron trihydride. Boron is a nonmetal. Hydrogen's a nonmetal, so this is covalent. Boron lives here in group 3. So go ahead and set this up. Boron in the middle, 3 hydrogens around it. Well, boron has 3 valence electrons, doesn't it? Hydrogen has 1. There's our boron. There's our hydrogens. Now, we can clearly make 3 bonds here, can't we? But, when we do this, this poor boron is stuck with only 6 electrons. And there is nothing we can do about that, is there? There is no trick we can come up with to make this poor boron happy. When we do acids and bases, we'll see that this is called a Lewis acid, which is an electron acceptor. There's BH3, a Lewis acid. Something gets a Lewis acid dearly wants electrons. This guy doesn't have enough. And so it will accept electrons from almost anything. BH3 tends to, in the lab, you get what's known as BH3 etherate. This is an organic ether, a dimethyl ether it's called. And the oxygen has 2 unshared pairs of electrons. When you put the 2 together, one of these unshared pairs donated, or shared, if you will, with the boron to make this complex. Here's another view of it. This is a coordination complex. It's called coordinate bond. You're actually supposed to use a little arrow because both electrons come from one atom, none from the poor boron. Any questions? All right, well that pretty much winds up covalent bonding. Let's go ahead and look a little bit more at ionic bonding. Like I said before, we're going to form cations and anions. We do this by totally transferring an electron from, say, sodium, loses 1 electron, chlorine accepts 1. That means that sodium has the same configuration now as neon. Chlorine has gained 1, so it goes up to argon. So they're both full. Again, this is the sodium cation and the chloride anion. They always occur in a fixed ratio. 1 positive, 1 negative. They're held together simply by electrostatic attraction. And if you've ever seen a big crystal of sodium chloride, you see that it's nicely cubic. Even salt grains under a microscope are cubic, little tiny cubes. And that's because when you pack the positives and negatives together here, they tend to pack in a very organized way, and this just happens to form little tiny cubes. Keeps growing until you get a huge crystal. Anions and cations can have charges ranging from +1 to +4, or -1 to -3. Again, we can just simply look at a periodic table and predict what they'll be. Our first 4 are very simple. It's simply the group number, 1, 2, 3, 4. For the anions, what you want to do is look at the group number and see how many electrons you have to get over here to group 8. So if we're in group 5, we're going to be a -3, a -2, and then a -1. So that's how you can figure out for a given compound the charge on the ions. Now when you go to build a compound, you have to follow what's called the principle of charge balance. That basically means that the compound that you're going to build must be neutral. Okay? It must be neutral. If we take one magnesium is in group 2, so it's a +2. Sulfur is over here in 6, so it'll pick up 2 electrons, that's -2. This is 2 pluses, 2 minuses, and the net charge is 0. Sodium and bromine, 1 plus, 1 minus, and we're 0. Now if we have an anion, like sulfide dianion, 2 negative charges, and we're pairing it with sodium, we need 2 of them to neutralize the charge. 2 positives, 2 negatives, again we're 0, and the same thing in reverse. 2 positives, 2 negatives, and we're at 0. To write a formula for an ionic compound, what you want to do is to write the cation and the anion in the simplest whole number ratio. So here we have 1 magnesium and 1 sulfur. We would simply write this as Mgs. If you had written it as Mg2S2, it would still be neutral, wouldn't it? But it'd be wrong. Lowest whole number ratio. Sodium bromide. Here we have 2 sodiums, 1 sulfur. So again, we use our subscript to show there are 2 sodiums to 1 sulfur. We have 1 magnesium, 2 bromines, magnesium bromide. When we talk about an ionic compound, what we're talking about is the formulas that we've written, lowest whole number ratio, to get our neutral structure. The unit is actually called a formula unit. Most people will slip up and call these molecules, but they're not. The term molecule is actually reserved for molecular compounds. Although, to be quite honest, nobody in the world uses formula unit. They just call it sodium chloride or whatever. But that's what the thing means. Again, reading this, 1 sodium, 1 chlorine, 1 hydrogen, 1 fluorine, 2 hydrogens, 1 oxygen. This is sulfate, isn't it? SO4. Remember? So this is potassium sulfate. 2 potassiums, 1 sulfur, 4 oxygens. Any questions? All right, let's look at a periodic table and just build a couple simple molecules, compounds, ionic compounds. Let's do magnesium and chlorine. Now, step 1, we want to find them on the periodic table, right? Magnesium is here in group 2, so it'll be a +2 cation. Chlorine is here in group 7. It will form a -1 anion. Next, what you have to do is come up with a ratio of magnesium and chlorine that's going to give us 0 charge. Now this is simple. If we have a -1 here, +2 here, we're going to need 2 chlorines for every magnesium. So we would simply write it like that. Once again, if you did Mg2Cl4, it would still be neutral, but it would be wrong. Let's do aluminum and oxygen. Aluminum is here in group 3. Oxygen is in group 6. So we have a +3 and a -2. What you have to do is come up with a ratio where the two cancel out and they're neutral. Zero charge. There's actually a trick to doing this. What you do is just write down what you've got. Aluminum +3, oxygen -2. Okay? This is a little symmetry operation. We're going to make aluminum oxide here. The charge here on the aluminum is going to wind up as a subscript here on the oxygen. The charge on the oxygen winds up as a subscript on the aluminum. And so just by inspection, it's Al2O3. Think about it. This is 6 positive charges, 6 negative charges. Let's do another one. Beryllium and selenium. Beryllium lives here in group 2. Selenium, where is it? Oh, here it is, in group 6. So we're going to have a +2 and a -2. Now the reason I did this one is, what if you really like the little algorithm that we just did, and you say, okay, I'll take Be and Se, simply cross the charges over, I get Be2, S2, Se2.
I can't see it.
But that would be wrong, wouldn't it? Because it has to be the lowest whole number ratio. So pay attention to it this way. The method works best if you have different charges. BeSe is what it should be. Any questions?
Confusing.
Yeah, how did you get?
Where are you getting the tubes from? Where are you getting these tubes from?
Well, beryllium is here,
Group 2.
group 2, so
Okay.
that's a +2. Selenium is here in group 7. It needs 2 electrons to get over to krypton.
Oh my God.
So it's a -2.
So you
Things
look
in
at the groups
Group
and
6,
then.
I'm sorry. 6 + 2 is 8.
So you're looking at the groups and then what?
For the first 4, you are going to simply do +1, +2, +3, +4.
Mm-hmm.
Okay? For the last groups here, remember we have to get from here over to our inert gases. And so we do group 5 by adding 1, 2, 3 electrons. Group 6 by adding 1, 2 electrons. And group 7 by adding 1 electron.
Okay.
So this is -3, -2, -1. However many electrons it takes to get over to the inert gases. Now, as we've done all of these things, I've been naming them. I'm sure you're sitting back saying, gee, I wish I could name them too. Well, it's actually very simple. The name has to contain both the cation and the anion. It's going to be 2 words, 2 separate words with a space in between. First word is simply the cation. Sodium, potassium, cesium, whatever. Just the name of the cation. The second name is the anion. Again, we're going to take the root of the element and we're going to add IDE to it. If we have more than one anion or cation, we do not use multipliers. Okay? So, here we have magnesium. That's our cation. So for our name, we write magnesium, space. For bromine, our root is going to be brome. We take our root, we add IDE, and this is magnesium bromide. You don't use a multiplier to say that there are two bromines, just do bromide. One sodium, one chlorine. Sodium is the cation. Chlor is our root here, and we will simply add IDE and make it chloride. K is potassium. No multipliers, even though there are two of them. Sulf is our root, and we add IDE. Be is beryllium. That's our first word. We've already done bromine. That brome is our root. And we add IDE. Now that's really simple, isn't it? All you have to do is name the cation, figure out, make your best guess for the root for the other element, and add IDE. Do not use multipliers. Go ahead and do this set. Ca is calcium, isn't it? Our root here is brome. So this is calcium bromide. Al is aluminum. The root for oxygen is ox. So this is aluminum oxide.
If I would have said aluminum oxygen, would I have been wrong?
Yep. Has to be oxide. The IDE tells you it's an anion. Li is lithium. This is sulfur. The root is sulf. So this is lithium sulfide. Ca we know is calcium. Here's oxygen. Its root is ox. Calcium oxide. Ni is nickel. Nickel is a transition metal right here. So a metal. Paired up with chlorine, we could call this nickel chloride. Well, we could call it nickel chloride, but we'd be wrong. We'll see that in just a few moments, but the reason is, as nice and predictable as the main groups are in terms of charges, lots and lots of transition metals can have different charges. So you have to tell what the charge is. This would actually be written nickel 2 chloride, where the Roman numeral 2 indicates that this is a +2 ion. But we'll talk about that in a minute. Now, as easy as it is to name something, because you don't have to worry about multipliers, if you go backwards with an ionic compound, you have to think. Go ahead and write the formula for these guys. Now what you have to do is to think about the cation first. Find it on the periodic table. See what its charge is going to be. Then you look at the anion. Find it on the periodic table. See what its charge is going to be. Then you must come up with a ratio so they're neutral. Let's just do our first one, so we get it. Calcium is here, it's in the second group. So it is a +2. Nitrogen's over here in group 5. So it needs 3 electrons to get over to 8. Therefore, it's a -3. So the first thing you do is say, okay, I can do this. +2, -3. Come up with a ratio that's neutral. This is where you could use your little crossover nicely. The charge here is -3, that means we're going to need 3 calciums. The charge here is +2, so we'll need 2 nitrogens. Magnesium is group 2, so it's a +2. Oxygen is group 6, so it needs 2 electrons to get to 8. So it's a -2. What have we got here? +2, -2, simply MgO. What group is lithium in? It's in 1. What group is iodine in? 7. So this is going to be +1 and -1. Looks like little, but it isn't. Barium phosphide. Find barium. Barium is right here in group 2. Phosphorus is over here underneath nitrogen in group 5. So phosphorus needs 3 electrons. It'll be a -3. Barium is a +2. Doing our crossover. If this is -3, we need 3 bariums. +2, we need 2 phosphorus. And finally, beryllium fluoride. Beryllium, the E, right up there. +2. Fluorine is over here in group 7, so it needs 1 electron, -1. +2, -1, need 2 fluorines, and there we go. Now let's really make it fun. And let's do this with our polyatomics. I know you haven't had quite time enough to remember all the polyatomics yet, but you will.
No.
Yeah, you will. So let's do these guys. Ca is calcium. That's simple, right? What was CO3? CO3 with a -2 charge. This is carbonate. Therefore, our name is simply calcium carbonate. The only positive polyatomic we had to worry about was NH4. We said that that was ammonia. So as our cation, that comes first, ammonia. Chlorine is the other thing. This is +1, -1. So this is just ammonium chloride.
Sorry.
What was SO4? 2-. First one we ever looked at. That was sulfate, wasn't it? Sodium is our cation. Sulfate is the anion. Sodium sulfate. If we take the parent here and take one oxygen off, what do we get? Sulfate down to sulfite, right? So this is going to be lithium sulfite. Now here we took phosphate, which is PO4, and we stuck a hydrogen on it. Right? So this is going to be hydrogen phosphate. Potassium is our cation. We simply write potassium hydrogen phosphate. Let's go backwards.
This one's different.
I told you probably would see this one every now and then. That's permanganate. Permanganate on our table was MnO4 with a -1 charge. Now, potassium is our cation. It's group 1, right here. Therefore, it is +1. Write the formula. We simply do potassium as a K and MnO4.
Isn't it a way of remembering how to pronounce it based off the numbers, like 8, like the ATE at the end would be like for 4s and
Nope. No, it can be 3, 4. I think either 3 or 4. But barium sulfite. Barium is a +2. It's a group 2 metal. It's a +2. Sulfite, we remember, has 1 less oxygen than sulfate. So it's SO3. We have a +2 and a -2. Barium sulfite. Chlorate was the parent for the chlorine group, right? This is a ClO3 with a single negative charge. So it's a -1. Aluminum, however, lives all the way over here, and it's a +3. So to get neutrality, we need 3 chlorates for every aluminum. Now when you write this as a formula, to make sure that it's clear that you have 3 separate chlorates, what you have to do is put the chlorate in parentheses and then indicate that we have 3 of them. Silver nitrate. Silver is actually a transition metal, but it's one of the few, silver and gold, that really only carry 1 charge, and they're both +1. So you don't have to indicate the charge on silver. It's always 1. Nitrate, we remember, was a parent. It's NO3 with a single negative charge. And finally, cyanide was the other one I told you probably would see. Remember, it's Cn-. Barium is a +2. Cyanide is -1. Therefore, we need 2 cyanides for every barium. Remember, that has to be in parentheses. Think about it, if we didn't have our parentheses here, it would be BaCN with a 2. That would look like 2 nitrogens, wouldn't it? Doesn't make sense. All right, now if you're feeling a little overwhelmed with
Yes.
the polyatomics, no, I'm sorry, but I don't care. I know what they are. No, not really. Of course I care. Remember, on the exam, you get to bring a 3x5 card. Okay, with anything in the world you want written on it. And if you want to waste your card writing polyatomics on it, be my guest. Okay?
Do you know how small I'm gonna write on my card?
Right, everything from chapter
Really,
1.
really
Oh.
small.
Yeah, so
You know, the real learning.
oh, you need a
Bring a
magnifier.
magnifying glass.
Like this. By the time you sit there and you concentrate and write them really small, you know, pay real close attention as you're doing it. By George, when you finish writing your card out, you know them already.
Does it have to be a 3x5?
Get a sheet of paper.
No,
Does-
3x5.
It's gotta be a 3x5, it can't be one of the bigger ones?
No.
Right.
All right, let's do a couple simple ones here. Just go ahead and quickly name these compounds. Pb is lead, Fe is iron.
Then lead oxide. Then
Yeah, I'll be looking into it.
oh,
Well, our first one, we have a lead and an oxygen. That's lead oxide, right? Don't use multipliers because they have metals, they're ionic. So the next one is lead oxide. Oh, gee, yeah.
really?
This is an iron and oxygen. No multipliers, this is iron oxide. And so is that, and so is that.
Oh, so it's just
Obviously, we have a problem here, don't we?
yeah.
That's because lead and iron are
Are
in
in
the
the
transition metal
transition
bond.
metals.
What's varying here is what's known as the oxidation number. Oxidation number is a fancy word for charge. What the oxidation number really tells us, officially, is the difference between the element as you see it here and the element in the compound. For most simple cations, you're gonna lose some electrons. So the oxidation number is gonna be positive, gonna be 1, 2, 3, or 4. If we look at a couple very simple compounds, this magnesium and bromine, not a transition metal, is it? But we can still talk about it as an oxidation number. The charge here is a +2, charge here is a -1. Therefore, if we wanted to call these oxidation states, we would say the oxidation number is +2 and bromine is -1. Simply another way to talk about the charge. For lithium phosphide, this is a +1, that's a -3. Oxidation numbers would be +1 and -3. Same as the charge. Now, oxidation numbers are used in lots of areas of chemistry. We may talk about some of them later. But for right now, let's just look at the rules. And then I'll show you which rule you need to worry about. If we're dealing with a pure element, it's always defined as 0 because it's exactly like it is on the periodic table. If we're in group 1 or group 2, it's always going to be 1 or 2. Fluorine, over here in group 7, is always going to be -1. If we have an ionic compound or a metal hydrogen compound, it'll be -1. Otherwise, hydrogen is always +1. Here's what you need to remember. Oxygen is going to be -2. Halogens are going to be -1. Those are the two parts of the rule that you need to remember. Okay, so let's go back and look at some compounds. Here are 2 of our lead oxides. What we want to do is simply apply the rule to figure out the charge on the lead. The rule said that oxygen was always going to be a -2, right? If this is going to be neutral, what's the charge on our lead? +2. Here we have 2 oxygens, and they're -2 each. So that's 4 negatives, right? So what's the charge on our lead? +4. Let's do our iron compounds. This one wasn't on our list. This is sulfate, isn't it? But what's the oxidation number of the iron? Well, sulfate, we all remember now, is -2. If this is neutral, the iron must be +2. Oxygen, we know, is always going to be -2. We have 3 of them. That's 6 negatives, right? We have 2 irons. In order to make this 6 positives, the iron must be +3. All right, let's finally work this into our nomenclature. Remember the example we saw with nickel. We're going to show the charge in parentheses in Roman numerals. That's all. So here we have lead oxide, right? We have 2 oxygens, that means this lead must be +4. So we would write it lead 4 oxide. No space between lead and the parentheses, put a space here. Lead 4 oxide. Here we have 1 oxygen, it's a -2, this is a +2. So this is lead 2 oxide. CO3 is carbonate, right? -2. If carbonate is -2, iron must be +2. Iron 2 carbonate. And finally, bromine, halogen. Remember, those are the halogens. All halogens are going to be -1. Therefore, this is iron 3, must be +3, to have 3 -1s here. Now that's really fun, isn't it? It is. And so, of course, there's a tutorial. The tutorial here. This is nomenclature of binary ionic compounds. That simply means there are only 2 things. Here's our formula. Ba, what's Ba?
Barium.
Barium. I is iodide, right? Barium is here in group 2, so we don't need to put a charge, because they're always going to be 2, aren't they? Therefore, for our name, we would simply say barium iodide, and we got it right. Do this one. Copper is a transition metal right here in the middle, so we have to show the charge. I is simply iodide, isn't it? It's a halogen, so it's a -1. If iodide is -1, copper must be +1. And you would simply write it, copper 1 iodide. Look at your table of polyatomics. What's ClO? Chlorate was our parent. We took 2 oxygens off. What does that make it? Hypochlorite. Hypochlorite. Clorox is sodium hypochlorite. All right. The charge on hypochlorite is -1. Therefore, what's our charge on our iron? +3. Because we have 3 of the hypochlorites to make it neutral. So this must be +3, and we have 3 -1s here. So this is going to be iron 3 hypochlorite. Any questions? All right. Well, then let's move on to molecular compounds. You know how to name ionic compounds, right? How do you name a molecular compound? It's going to be essentially the same. The difference is, there we're going to use multipliers. The multipliers we use, 1 is going to be mono, 2 is di, 3 is tri, tetra, penta, hexa, hepta, octa, nona, and deca. Now you're probably never going to see things here. You see 7, 6 and 7, and 5s and stuff, all this. But those are simple to remember. Mono, di, tri, tetra, penta, hex, and hept. Okay, we're going to do the same thing. The first element is simply shown with its name. So, carbon. Our second element, we're going to take the root. If it was CO2, we would take the root. We would say it's oxygen, so it's oxide. But because there's 2 of them, we would call it dioxide. Let's just do some examples here. 1 carbon and 4 chlorines. It's a molecular compound, isn't it? Because they're both nonmetals. What's the first word of our name? Carbon. Duh. Now the root for chlorine is chlor, right? So we're looking at chloride. And how many are there? 4. Carbon, tetra, chloride. 2 words. SO2. Molecular compound, they're both nonmetals. First word is just the element, and that's sulfur. We're dealing with oxide, and there are 2 of them. This is sulfur dioxide. Actually, let's go back to this. I forgot to mention this. When the first element only has 1 of the element in the compound, so this is 1 carbon, 4 chlorines, we do not use mono, okay? Just the element. So this was carbon tetrachloride, not monocarbon, and this was sulfur, not monosulfur. All right, here we have 2 nitrogens. So here we have to use a multiplier for our first element. So it's nitrogen, and there are 2 of them. We simply call this dinitrogen. Now, when we only have 1 of the second element, that's when you, and it's an oxide, that's when you have to use mono. So this is monoxide. The second O we delete because it's too many O's. This doesn't look right. How about this guy? Dinitrogen again, isn't it? That's simple. And what's 5? 5 is a pent, isn't it? So we're dealing with oxygen, so it's a pent oxide. Again, penta, if you're dealing with something that's not a vowel. But when you have two together like that, just dump the A. It just doesn't sound right. All right, let's go ahead and do a list. Quickly, jot down names for these guys. Carbon is our first, isn't it? This is oxide, we have two of them. This is carbon dioxide. We have two of the first. We have to use our multiplier, di. So we have two hydrogens. We would just call this dihydrogen. Now we only have one sulfur, so we have to use our multiplier. So this is monosulfide. One silicon. So silicon is our first word, right? Our multiplier for 4 is what? Tetra. So this is hydrogen, that becomes hydride. So this is silicon tetrahydride. One sulfur, 3 oxygens. First word is sulfur. Multiplier for 3 is tri. Sulfur trioxide. 1 nitrogen. 3 chlorides. Nitrogen trichloride. Now you have to remember, let's go ahead and do another set. I've got another set here. Some of these are a little more interesting. Go ahead and just do these. Multiplier for 6 is hex, remember. Hexa. We had 4 phosphorus. Our multiplier was tetra, right? Tetra phosphorus. Hexasulfide. Seven is a hepta. So this is diiodine. Hept oxide. Drop the A out. Now, you know, if this was a test and you put the A in, I wouldn't care. Okay? So, don't get paranoid about that. Oxygen is our first element. We have 2 fluorines. That's a difluoride, isn't it? We've seen this guy many times. This is methane, isn't it? But it has a real name. 1 carbon, so it's a carbon. 4 hydrogens, it's a tetrahydride. And finally, 4 sulfurs would be a tetrasulfur, wouldn't it? 2 nitrogens, dinitride, and there it is. Now, remember what a pain it was to take an ionic compound by name and go back to the formula? Well, this is so simple because the name tells you exactly how many copies of everything there are. Go ahead and do them.
Oh, God. I've got 60 cramps in my head. I got migraines, cramps, everything, confusion, everything.
All right, nitrogen triiodide. Nitrogen's our first element, that's an N. And we simply have 3 I's, right?
Mm-hmm.
Gosh. Nitrogen triiodide's a really neat compound.
This is not the easiest thing.
We'll look at that, look at a really neat video of that. It's a contact explosive. In a little video, it's got a little thing, you touch it with a feather, and it explodes. Diphosphorus pentoxide, we have 2 phosphorus, so that's P2, right? Pentoxide, we have 5 oxygens.
Dr. Young got keys.
Oh, sorry.
Oh, yeah. Thank you.
1 sulfur, 3 chlorines. One nitrogen, 1 oxygen. No. No. 1 hydrogen, 1 chlorine. Later we'll realize that this is hydrochloric acid. All right. I forgot, well, I didn't forget, but at the last moments before class, I added these tutorials in. Turns out that there are 2 other tutorials that you might want to do. This is formula to name for molecular compounds. And what you do here is you are given a formula, and you simply type the name in. Capitalization doesn't matter, but you have to spell it. Remember, if you need a multiplier, make sure you put it in. So what is this guy? Dinitrogen trioxide. All right, what is this one? Monosulfide, right, that's good. And there's another one. Names to formulas. This one is a mixture of ionic and molecular. 1 sulfur, 4 bromines. Now, when you write the formula, you can't do subscripts. So you just have to just put the number. And again, if you had something like a sulfate up here,
I'll go to church.
parentheses.
Going to
One
church
more.
on, shoot.
Sodium phosphate,
Lord and I are gonna be best friends for life.
Yes.
phosphate is PO4. It is a -3, isn't it?